So in the slides that follow, we're going to explore 3 use cases: estimating an engine's remaining useful life, predicting if a water pump is in need of service, and identifying if a celestial object is an exoplanet. With each use case, we have 2 goals. So 1, to demonstrate how SML serves as a solution to an example of a problem structure that is common across multiple domains. And 2, to show how models in SML are not black boxes and can be used to derive insight. So use case 1. Our first use case is an exercise in predictive maintenance. Turbofan engines are a kind of jet engine widely used in aircraft propulsion. We wish to predict an engine's remaining useful life, or RUL, the number of operational cycles left until an engine will fail. To do so, we'll use synthetic data provided by NASA's Prognostic Center of Excellence. And these plots, particularly these panels at the top left, describe the learning task. In training, we're provided with information on 50 engine units that have been observed over time. At each cycle, measurements are collected from 14 sensors that describe the unit's changing state. Our goal is to ingest the sequential information from these many time steps of sensor measurements and output a single prediction of the unit's remaining useful life. The 50 training units have been run till failure. From this plot alone, you might have some intuition already about how to engineer features that flag an imminent failure. For instance, sensors 2 through 4 exhibit an upward trend as the fault grows, whereas sensor 7 trends downwards. Our strategy will be to use SML sequence encoding tool, which will automatically extract hundreds of statistical characteristics from each sequence. I will delve into this problem in greater detail in the live demo, but it's worth noting here that this feature extraction strategy, though very simple and quick to employ in SML, yields performance competitive with scientific papers that have achieved publication. Many of these papers employ deep learning, models whose architecture is typically time-consuming to define, is typically very problem-specific, and which typically takes an experienced data science and some computational horsepower to train. So use case 2. So Tanzania has a population of 58 million people, and it is estimated that 40% lack access to reliable, clean drinking water. Using data from the Tanzanian Ministry of Water, our task is to use a survey of 55,000 water pumps to build a model that predicts if a pump is likely to be functional or in need of repair. This table collects a few observations. For each pump, we have attributes describing qualities like the pump's mechanism, the water source, and water availability. By building a machine learning model in SML, we yield a test accuracy of 82%, which for context, matched the best of 34 teams that participated in a data science predictive modeling challenge. Our model outputs a probability that a pump is faulty, but SML also helps us decide how to respond to these probabilities. For instance, I might identify that it is better to err on the side of caution and dispatch a maintenance crew to any pump which the model suggests has a 15% probability or higher of being broken. On the other hand, suppose I am restricted by a tight budget constraint. In this case, I might dispatch crews to only those pumps with an 85% probability or higher of being in disrepair. We can visualize the error profile associated with a particular decision threshold using a confusion matrix. A confusion matrix tabulates the counts of predicted first ground truth categories. So on the vertical axis here, we have the predicted categories, functional or faulty, and on the horizontal axis, we have the same for ground truth. For this confusion matrix, the decision threshold we used was 50%. The bottom left cell reflects the number of false positives. There are 848 false positives, cases where the model erroneously classifies a pump as being in good repair when it is in fact faulty. In the context of water pumps, this kind of error is particularly costly. We may wish to concede some false negatives represented in this cell in order to reduce the count of false positives. We can do this by tuning the decision threshold. We can visualize the error profile across all potential decision thresholds using an ROC curve. So an ROC curve plots the true positive rate versus the false positive rate. As we make the probability threshold more lenient, so as we travel up this line, we trade off between the false positive rate and the true positive rate. An ROC curve helps us identify which probability threshold strikes the optimal balance between the two. On the subject of water, Amphos 21, an environmental consulting company, recently partook and earned first place among 40 competitors in a challenge to predict the presence of pollutants in water. Their solution was created with the help of SML. Normally, the process of testing the water for high levels of contaminants is very time-consuming, where water samples are manually analyzed in the lab. Building a predictive model using existing data with SML, Amphos's team created a solution that can quickly identify pollution to help mitigate the risk of contaminated water infiltrating a wastewater treatment facility. Congratulations to them. We were thrilled to hear about their success. So our final use case 3, uses data from NASA's Kepler Space Telescope, which is an observatory in space dedicated to the exploration of new planetary systems. It is possible to find planets and even measure their size and temperature by inspecting variations in the brightness of a star when a planet transits in front of it. Here I want to use data recorded by the Kepler Space Telescope to train a machine learning model that can automatically detect an exoplanet. We're able to do so successfully in SML, yielding a test accuracy of 99%. So suppose now that you're an astronomer and are interested in determining the relationship between an object's radius and whether or not it is an exoplanet. An initial strategy might be to compare the distribution of object sizes for planets versus the same distribution for other objects. So indeed here we can see that larger objects tend to not be planets. However, this approach lacks rigor. Not only do we fail to quantify the effect, but we do not control for the presence of confounders. Larger objects may coincidentally be associated with higher values of other features that identify planets, which would bias our interpretation of the relationship. SML provides a solution. Using a partial dependency plot, we can quantify the effect a unit change in radius has in the probability an object is a planet, controlling for the effects of other features. Furthermore, we can infer if the relationship between radius and the target is nonlinear. For instance, when an object is very small, in this regime here, we might expect a marginal increase in size to make it more likely to be a planet, versus if an object is already big, perhaps we're in this regime, then if it gets larger, it may be more likely to be a different kind of object. A partial dependency plot is capable of capturing and representing that kind of complexity. With that, I'm going to transition to the demo. So we'll return to the problem of RUL prediction for turbofan engines. So please give me 1 minute as I switch panels. So welcome to SML. Sorry, quick question. Are you able to see my Firefox window? Okay, I'll take that as yes. Okay, so first we create an experiment. So as we launch an experiment, the first thing we notice is a progress bar. There are 5 milestones we will travel through to deploy our model. We begin with initialization, where our objective is to frame the problem. We do so in 3 clicks. First we select the data that we have previously uploaded. This will open a preview panel as well as establish a data signature. When we eventually want to apply our model to new data, the signature will remind us of what inputs we need. Second, we choose a target column. In this case, we want to predict remaining useful life, which is called RUL in the dataset. Finally, we specify whether our problem is a regression or a classification. Whereas regression problems tend to estimate a continuous value, classification problems identify which category an observation belongs to. SML has intelligently inferred that our problem type is a regression. We are ready to proceed to pre-processing. In pre-processing, there are 3 panels. The data panel offers us a direct view of our data, which we can navigate using filters in the column headings. The summary statistics panel provides useful statistics like mean, standard deviation, and missing values, all of which are helpful to inform decisions about pre-processing operations. Finally, the operations panel gathers several pre-processing operations, which we can utilize to transform our data and ensure it is well posed for machine learning. In the data panel, I begin by selecting the unit filter, and I can quickly inspect time series information from a single unit. So here, for instance, I'm going to select unit 1. And if we go to the end, we can see that unit 1 was run for a total of 56 cycles. And at cycle 56, it would function for 137 more cycles until failure. In the column summary panel, I observe that we have information on 150 unique units in total. When it comes to pre-processing operations, SML offers users 2 modes. In autopilot mode, SML will detect what pre-processing operations are best suited to your data. For instance, it will identify and treat missing values and convert categorical variables to a numerical representation. Autopilot can be run at any time and will intelligently respond to your actions and finish off pre-processing. After I execute autopilot, we'll be routed to the activity log, which you can see here. Oh, sorry, I left the app open for a little while. So it's okay. So here's the activity log. So we can see that a train test split and categorical encoding have been performed. I can also undo or redo operations. So here I'm going to undo categorical encoding of the unit column. In the column summary, we see evidence of the train test split operation. Whereas we initially had 150 unique units in our data, now we only have 50. 100 units have been held out in our test dataset and will be ultimately used to evaluate how well the model will generalize to new data. I can also opt to perform operations manually. We can use visualizations and to inform pre-processing operations and decisions. So for instance, with the distribution plot, I can plot histograms of the operation setting variables. So I'm going to choose operation set 1 and operation set 2. We see that the variables are mostly constants and resolve to drop them. Both of them are concentrated around 0 and have near zero standard deviation. So if I return to the pre-processing panel, I can select remove all features, and now I'm going to choose to drop these two variables. Great. Finally, we perform sequence encoding. So that's right down the bottom. I select the sensor data, and I also stipulate which columns we use to identify engine units and identify the time dimension, which in this case was cycle. I can also choose a false discovery rate. So this will manage how many features are created. So I'm going to choose -1.5 here. So if you're manually applying pre-processing operations, SML still offers guidance in the form of QC messages. Here, SML alerts me that I've used the cycle column in 2 column definitions and suggests that I deselect it from 1. So I'm going to remove it here. And you'll notice now that QC passes and we can proceed with the pre-processing operation. So this pre-processing operation will take some time to run. We're calculating hundreds of time series characteristics. However, SML accelerates this process by parallelizing it across several machines. I'll give it a few seconds for it to process. Great, and we're done. Pardon me 1 second. SaaS sequence encoding. Sorry, I think I failed to set this parameter correctly. Okay, we're ready now. Great. Great, so before we had a long data set where each row represented a unit cycle pair, now we have consumed the time dimension. You'll see that now we only have 50 rows, 1 for each unit, but we also have many columns created, which represent several time series characteristics. So here's a few of them now. So we're ready to proceed to model training. In model training, we begin by selecting a model evaluation metric. I'm going to choose R². Then we pick which algorithms we want to apply. A number of supervised learning algorithms are available in SML. Each is characterized by different heuristics for finding relationships between features and the target. These include tree-based methods like random forest and XGBoost, kernel-based methods like SVM, and even a fully connected neural network. So I'm going to choose a random forest and XGBoost. For each algorithm, there are a number of hyperparameter tuning decisions. We can manually select a hyperparameter space to explore, or use SML's recommended defaults in autopilot mode. In the course of model training, SML will perform k-fold cross-validation on the training set to select the best hyperparameter configuration. So I'm going to launch training for both the random forest and for XGBoost. So our hyperparameter search has now been distributed and has been crunched in parallel across multiple EC2 instances. As the model is being tuned, we see a live report of the evaluation metric. Metrics are reported for both validation and training data. We can also monitor tuning using the plot view. If our model's validation score hasn't improved in a while, we can choose to halt training early. We're now ready to proceed to model finalization. At this point, we have trained multiple models, and we have multiple to choose from. So which do we serve? We can select one. However, we can also elect to create a model ensemble. So I'm going to select multiple here. So ensembles in SML integrate the opinions of different models using a weighted combination. We can weight each opinion equally, or we can train a linear model to learn the best configuration. Those are the lasso and ridge models. I'm going to use a simple mean ensemble, which will combine predictions from our random forest and XGBoost. Great. So now we're ready to proceed. So at this point, we've arrived at the final milestone, the model playground. The playground is populated with different cards. In general, they fall in three categories: model review, model explanation, and deployment. So how can we conduct model review? Suppose I wish to compare two experiments or share an overview with a peer. The model scorecards publishes the evaluation results that we just saw, my training, test, and validation performance. Meanwhile, the review experiments card communicates a blueprint of all the steps that were taken to reproduce the model. We can also elect to generate a PowerPoint report. In the playground, I can also view model diagnostics. For regression models, we plot ground truth versus model predictions. The more densely data falls along the 45-degree line, the better the model is at the prediction task. This plot serves as a good sanity check and demonstrates how the model error evolves as a function of the target. Here, for instance, we see that the plot suggests that the model does a poor job at predicting very low RULs, and that we can observe that we probably need more training data in this region. The lowest value of RUL in our training data is about 42, and you can see that this is also the minimum prediction given by our model. Now let's talk about the cards related to model explanation. The main goal of model explanation is to bring a high level of transparency and trust to the supervised learning results. When an SML model generates a prediction, SML provides users the option to break it down according to each feature's contribution. We measure feature importance by summing up those contributions over many predictions. So I'm going to choose here to explain 50 points from our dataset. So for our model, we see that the most important predictor of failure is sensor 15, 17, and 11. So we can use, so to learn more about the relationship between these variables and RUL, we use the partial dependence plot. So here's where we can observe what the marginal effect of a unit change in, for instance, each of these features has on RUL values. So I'm going to choose, for instance, sensor 11's autocorrelation. So here we observe that the more positive autocorrelation is in sensor 11, the more imminent machine failure is likely to be. The goal of uncertainty quantification is to provide, in addition to our best guess prediction, a distribution describing the sensitivity of that prediction to sampling bias in the training data. Uncertainty quantification is executed by another internal machine learning workflow within SML, which I'm going to run now. As you can see, the results are a confidence interval that we were able to associate now with SML predictions. So this blue line represents our predictions, and the gray band represents an 80% confidence interval. Finally, let's talk about the cards related to deployment. Users have two options for making predictions. They can interact directly with the app using the Make a Prediction card. So here they can choose to manually upload a CSV. So for instance, we already have the CSV that we've trained our model on. Alternatively, they can manually input a prediction or a prediction task using the manually edit feature. Another option for actioning a model is to generate an API key. So select this option if you'd like to integrate predictions from a trained SML model into your production environment. As you can see, we provide sample code in a few different languages. So here's some Python code, and similarly, some JavaScript, which you can integrate into your production environment.